Hi guys, so we are going to start looking at how to find exact answers for integrals. So if you remember, we started the chapter out by finding exact answers, but only for specific functions where we could actually use geometry. So then we started looking at, okay, well, what happens when we can't get exact answers? So we used approximations using our rectangles and our trapezoids. So now we're going to look at, okay, well, if we take enough of those rectangles, we know that we can get an exact answer. If we make those subintervals super, super small, we know that we're actually finding a more exact answer. So we're going to look at how to actually do that now using antiderivatives. So before we can dive too much into antiderivatives, we need to look at the different notation that we use, okay? So we've got summation notation and we have integral notation. So this probably looks maybe at least a little familiar to you from Algebra 2, but this weird E here, all right, that we use with summation notation, this is called a sigma. And anytime we see sigma, we know that we are finding a sum. So what we're doing is we're saying if we get enough of these rectangles, we get this exact answer. Well, that means we want to add up and find the sum of a bunch of rectangles. All right, and more specifically, not just a bunch, but we want the number of rectangles to actually approach infinity. We want to say that there is an infinite number of rectangles on this interval. All right, so we've got these infinite number of rectangles. F of x is our function, so that gives us our y values. All right, when we looked at those approximations before, we said that the y values give us the heights of our rectangles. And then we also know that delta x is just giving us the base of our rectangles. And we want that to be super, super small because we want this infinite number of rectangles on this interval. All right, so the last thing I want to point out to you then actually is this interval. So we're saying we're on the interval from a to b, which means a is our starting x value, x equals a, and then we want to stop at x equals b. So what we're going to do now is we're going to talk about how this summation notation can actually be translated into integral notation, which even though it's new, we're actually a little bit more familiar with that. So what we're going to write right now is actually equivalent. It's the same thing as this limit notation, this summation we're using over here. So we're going to find an integral. And we know that our integral always has our start and our stop, so we want the bounds of integration, which are always going to come from our interval. So if we're starting at a and ending at b, then we're taking the integral from a to b. And then we want our function, which in this case is f of x. And if you remember, we said that we always need to close our integral with a dx. So anytime we see delta x, we're going to take that and change it into a dx when we change it to integral notation. So let's look at what this is going to look like for you guys. So on the AP exam, they will probably give you something that looks like this limit notation, and you have to be able to express it as an integral. So you need to be able to translate between these two types of notation. So taking a look at number one, we know that we've got this here and we want to translate it into an integral. So we need our integral and we need our bounds of integration. So we said that our bounds always come from the interval, which they give us right here in the problem. So we're going to find the integral from -1 to 3. And now we need to find our function. Well, our function is right here, but it looks a little funny. So you'll notice that it's got this m sub k, or for example in number 2 it's got this c sub k. So what that's giving us right there is the specific x values that we're finding the values of. So for example, this could be something like the midpoints on each interval. or it could be the right endpoints if we're using an RRAM approximation. So what you need to know is that when we translate to integral notation, those m sub k's or c sub k, whatever it happens to be, those are just our x values when we're in integral notation, which means the function that we're doing here is 3x squared minus 3x plus 5. And then remember, we need to close our integral notation, so this delta x right here is going to change into a dx at the end of our integral. All right, taking a look at number 2, we're going to do the same thing then. So we need our integral, and our interval is what gives us our bounds of integration, so we're going from 0 to 1. And we need to look at our function, which in this case is the square root of, we're going to change that c sub k to an x, so 4 minus x squared. And then to end our integral, we know that we need dx. So you're going to have to be able to translate from limit notation and the summation notation to integral notation. Now, before we get into truly these antiderivatives, let's do a really fast review of derivatives. So you guys know how to take derivatives. We've been doing it for a long time now. So if I want to take the derivative of this f of x, I know that f of prime of x is going to equal 2x plus 3. All right, for example 2, f prime of x, that's also going to be 2x plus 3. So what I need you guys to pull from this is that those derivatives are exactly the same. But look at the original functions. They are not exactly the same. They start out the same, but what we can notice is that they actually differ by this constant. So number 1 had a plus 8, and number 2 had a minus 100. But when we take the derivative, those constants disappeared. So I want you guys to make a note, f of x differs by a constant. But what that means then is when I take the derivative, now they're not different anymore. So that's going to be a really important piece when we start looking at the antiderivatives. First 3 and 4, you should see the exact same thing then. F prime of x for number 3 is just cosine of x, because the plus 8 has a derivative of 0. And for number 4, f prime of x is going to equal cosine of x, and the negative 10 just disappears. All right, so again, that's going to be really important when we start looking then at what these actual antiderivatives are. So an antiderivative is a term that we use to describe the reverse process of taking a derivative. So for example, if f of x is equal to x cubed plus 8, then f prime of x, we can just use some really quick power rule and we get 3x squared. But now when we're going backwards, f prime of x is 3x squared. If I want the antiderivative, then that has to be x to the third plus c. All right, so let's talk about what this plus c means. Well, on the last page when we looked at those review examples, I pointed out to you that the constant term always disappears when we take the derivative. That's because the derivative of a constant is always 0. So what this means is we cannot determine the value of a constant just by looking at the derivative. So we write this plus c as a placeholder for the unknown constant value. When we took the derivative up here, this plus 8 disappeared. So when I'm taking the antiderivative, I need to acknowledge that there was a plus something there. All right, it's just that I can't figure out exactly what it is without more information. So this plus c is going to be super important when we take these antiderivatives. All right, let's look at some rules for finding antiderivatives. So these first two should be ones that you were able to kind of pull out in our investigation in class today. If f prime of x is some constant k, all right, then we know that the antiderivative is f of x equals k times x, so kx, plus c. So for example, if f prime of x is equal to 8, then the antiderivative is f of x equals 8x plus c. So if our derivative is just a number, then we know that the antiderivative is some type of linear function with the slope being whatever that constant value is. All right, and we can always check ourselves. We can just take the derivative. So if f of x is 8x plus c, then f prime of x is going to be 8, the x is going to disappear, and the c is going to disappear. So we know that we're correct on that. All right, now this second one looks a little messy when we write it out, but it makes a lot of sense when we actually go through it. So if we've got this polynomial function, what you need to think about is we are undoing the power rule. So we used the power rule even up here on this example, right? We had x to the third, so we dropped the exponent and multiplied it in front, and then we subtracted 1 from the exponent. So now we're going to be doing the opposite of that. All right, so I want to go ahead and start by actually doing that. So f of x, I'm going to leave some space because I'm going to start by actually adding 1 back to my exponent. Because when I'm doing a derivative, I subtract 1. So antiderivative, I want to now add 1. Now normally when I'm taking the derivative of a function and I'm using power rule, I'm going to drop this exponent and multiply it in front. Well, since I want to undo that, I'm going to need to divide by that instead. And then whatever my constant was in front is just going to be on top. All right, so I know it looks a little funny, but let's look at an actual example then. So if f prime of x is 4x squared, then we know, oops, I forgot my plus c. See, even I do it sometimes. Sorry guys, put that in there. So our antiderivative is going to be f of x equals, we're going to take x squared, and we know we want to add 1, so it becomes x cubed. Now think about taking the derivative of x cubed. It would have to be 3x squared. But this isn't a 3, there's a 4 here, which means this is going to have to be 4 over 3. And then we need our plus c. So let's take a little bit of a closer look at that. My new exponent here was a 3, and I needed to divide by that same number. All right, so that's this n plus 1. That's my new exponent, and I need to divide by my new exponent because I'm undoing the power rule. All right, again, you can take the derivative and check it. The next one is looking at powers of -1. So this one here is very important for you to be careful of. All right, because we cannot undo power rule here. Because it's not the same thing. A lot of students look at this and they go, oh, well, 1 over x is the same as x to the -1. So if I want to undo the power rule, then that means I would have to add 1 to my exponent, and I would get x to the power of 0, and I would have to divide by my new exponent, which is 0. And we know that that's not allowed. We can't do that because we're not allowed to divide by 0. So the thing you have to remember is we're finding an antiderivative. All right, well, antiderivative means which function gives me this as a derivative. So you need to think back to all of your derivative rules that we learned back in chapter 3. Hopefully you remember that the function that gives us a derivative of 1 over x is actually the natural log. So the antiderivative here is f of x equals the natural log of the absolute value of x plus c. And yes, it needs to be the absolute value of x because we can't have negative exponent or negative x values inside of a log. All right, so let's take a look at this example. F prime of x is equal to 3 over x. Well, when we look at that, we should be able to recognize that 3 over x is the same as 3 times 1 over x. So if I want the antiderivative, it's going to be f of x equals 3 times the natural log of the absolute value of x plus c. All right, this is one that you're going to have to be very, very careful of. Do not fall into the trap of trying to undo power rule. You have to remember all of your derivative rules, which is why the next part of the video is going to be super important here. We're going to race through all of the rules that we learned back in chapter 3. So if you learned them back then this should not be something that's super difficult. But if you had trouble learning them back then this is going to be something that is very difficult for you. So you need to learn them now. So again, we're talking about these antiderivatives, which means we want to look at the derivative that we have and think about which function gives us that derivative. So if f prime of x, if the derivative is sine, then we need to think about what function gives us a derivative of sine. Well, we know that cosine of x gives us a derivative of negative sine of x, which means I need to make this a negative cosine of x in order to make it a positive sine. And then we need to add plus c. If I want my derivative to be cosine, then my antiderivative is f of x equals sine of x plus c. We know that if we want the derivative to be secant squared, then the original function must be tangent of x. Secant times tangent, hopefully you recognize that as secant of x plus c. And then we need to be careful here, cosecant of x times cotangent of x. The normal derivative that we would see would actually be a negative cosecant cotangent, which means our original function, our antiderivative, must be negative cosecant of x plus c. And then cosecant squared of x, again, we're used to seeing actually a negative cosecant squared, which means our original function here must be negative. So f of x must be negative cotangent of x plus c. The hardest part here is just going to be keeping your negatives straight, but if you know your trig derivatives, then all we're doing is going backwards. Okay? Now let's look at exponential and logarithmic functions. So if f prime of x is e to the x, then the antiderivative is f of x equals e to the x plus c. That one's always kind of our favorite because it's the same going forwards and backwards. This one we talked about already, but it's so important that we are going to write it again. If the first derivative is 1 over x, then we know the antiderivative is the natural log of the absolute value of x plus c. If f prime of x is 3 to the x, then the antiderivative is going to be f of x equals, now this one's a little bit trickier. We know that if we have a function 3 to the x, then the derivative is 3 to the x times the natural log of 3, because we need to multiply by the natural log of the base. So since we're undoing that, we are going to then divide by the natural log of 3, and then we are going to add c. All right, and then this one looks funny, but we should be able to recognize that there's a derivative of a log going on there. So f of x is going to be log base 3 of x plus c. All right. Then we need to look at our inverse trig functions. So for this first one, we know that f of x is going to equal inverse sine of x plus c. And then if we have 1 over 1 plus x squared, the antiderivative of that would be tangent inverse of x plus c. 1 over the absolute value of x times the square root of x squared minus 1. Hopefully you can recognize that as the derivative of secant inverse. And then every single one of these over here is just the negative of all of these 3, which means these are all of my co-functions over here. So for the first one, it's f of x equals negative cosine inverse of x plus c. The second one would be cotangent. I don't know why I put negative, sorry. That's a positive cosine. This would be cotangent inverse of x plus c. And then the last one would be the cofunction of this, which would be cosecant. Inverse of x plus c. So again, if you know your derivative rules, this should be fairly easy. If you don't know your derivative rules, you are going to need to make sure that you get those memorized, because you're going to have to be able to pull apart a function and put these antiderivatives in there. And if you don't know the derivatives, that's going to be difficult to do. So let's take a look at one example really quick. So find the antiderivative of the following function. So when you look at this, you should hopefully be able to see four separate pieces. So I see 3e to the x, and then I see minus 5x to the 1/2, and then there's a 1/2 secant x squared, and there's a minus 1 over 1 plus x squared. All right, so we're going to take a look at each piece individually. So f of x is going to equal, well, if I have 3 times e to the x and I want the antiderivative, that's actually just 3 times e to the x, because e to the x is our nice simple function that we don't have to worry too much about. Then when I look here, I've got minus 5x to the 1/2. Well, that is a polynomial, so I'm going to be undoing the power rule. So I'm going to take my variable first, and I want to add 1 to my exponent. So 1/2 means I need to be adding 1, and I get 3/2. I have the 5 in front, and I would need to divide by my new exponent. Well, dividing by a fraction is the same as multiplying by the reciprocal. So I'm going to go ahead and put a 2/3 in front here. All right, that's my power rule. Then I have plus 1/2, and we need to know what the antiderivative of secant squared is. So what function gives us a derivative of secant squared? That would be tangent. And then the last piece here, negative 1 over 1 plus x squared, well, we just did that one. That would be cotangent inverse of x. And then we know that we need a plus c at the end, because we always need our plus a constant. Now it does say to check yourself over here on the right. I like to do it underneath my function, because then I can kind of see how each piece plays out. So let's go ahead and take that derivative really fast and make sure that we are correct. Oh, and actually, you know what? I need to simplify that. So let's do that first. So f of x is going to equal 3 times e to the x minus, this is going to become 10 over 3 x to the 3/2 plus 1/2 tangent of x plus the inverse cotangent of x plus some constant c. Now let's go ahead and check ourselves by taking the derivative. So f prime of x is going to equal, well, 3e to the x, the derivative of that is just 3e to the x, minus, I'm going to drop my 3/2, so I have 10/3 times 3/2, x to the, if I want to subtract 1, I would get 1/2, plus 1/2, the derivative of tangent is secant squared of x, and then the derivative of cotangent inverse is going to be minus 1 over 1 plus x squared, and the derivative of a constant is 0, so I would have a plus 0 here. And then I can just go ahead and simplify. So 3e to the x minus 5x to the 1/2 plus 1/2 secant squared x minus 1 over 1 plus x squared. All right, and we can see that that's exactly what we started with originally. All right, I know this video ended up being a little bit longer, but these rules are super important. You've got to have them written down so that you can study and make sure you know how to find the antiderivatives of all of these different functions. We are going to do tons of practice with this in class, so I will see you guys later.